Problem 27, page 706. Here we have a thin spherical shell. When I say thin, it means the internal of the internal radius equals to the external radius. The thickness of the shell is very small, tiny. When, like a football, the thickness of the football is very small in relative to the total radius. Okay. Here we have the radius of this shell equals to 14 centimeter. It's a thin spherical shell. It means that the internal Rn equals to R external. Let's say equals to R 14 centimeter. We can say here is the spherical shell with a very small thickness. The total charge Q equals to 32 microcoulomb. Micro, it means 10 power minus 6, okay? Equals 32 times 10 minus 6 coulomb. Find the electric field at 10 centimeter and at 20 centimeter from the center of the object. Here we have the center O. We have a radius of 14 centimeter. I want to calculate the field at 10. Let's say here we have a point. And also we have to calculate at a distance equal 20. Here we have 14 centimeter. Here we have 10. Let's say we have a point A, and here we have a point B at 20 centimeter. Okay. We said in the last video that in the case of empty shell, the field created at any point must be equal to 0 if the shell is positively or negatively charged. In the two cases, at any time, at any point, at any position inside the shell, the total field must be equal to 0. Under the condition, it's an empty shell. Okay, so the point A, the field at the point A equals to 0. Okay, we don't need to say why. Just is a empty shell E equal to 0. B, at the point I want to calculate at B. You know, also in the last video I said in the case of a sphere or a shell, the field, this object can be considered as a point charge. Okay, so we can say this shell is or can be considered as a point charge. So we can say here like a point charge. Here we have a point charge at the point O, and the Q equals to 32 times 10 minus 6 Coulomb. It's the same. And the distance between these 2 points equal to 20. So we can say E at the point B equals to K Q divided by the distance between the center of the shell and the object. Don't forget, here we have a shell. Just this shell can be considered as a point charge. The same result. Okay? So equals to K. You know that K equals to 8.9 99 times 10 power 9 times 32 times 10 minus 6 divided by the distance square. Don't forget to put it in meter, 0.2 meter square. The answer will be 7.19 times 10 power 6 Newton per Coulomb. Okay, this is the field at the point B. Maybe you can use Gauss's law to calculate this field, but it takes time, and we don't need to waste your time. Okay, in the exam you don't have time to do the calculation in the case of a shell or a sphere or any object, spherical object. At the field at any point external the object, the sphere must be equal kq divided by r square. Okay, if you want to use Gauss's law, you have to take a Gauss's surface at the point B, and you do the calculation. Okay, let's say you want to use Gauss's law, second method. Okay, here we have the shell, and you want to calculate at the point B, which is located at 20 centimeter from the center. In this case, you can use Gauss's surface, which is a sphere. Okay, let's say like this. Okay, it's second method, but it takes time. Okay, so we use a sphere of radius r as Gaussian surface. You have to say before bisymmetric. Okay, by symmetric. You know, at the surface we have dA must be out, and the field created by the shell must be out because it's positively charged. So also E must be out. We can say E parallel to dA. E is radial. E is constant at any point on the sphere. After this, we can say the total flux created equal the integral of a closed Gaussian surface E dA equals to Q n divided by epsilon. This term concerns the Gaussian surface. E is constant at any point, and the angle between E and dA equal to 0, we can say here equals to E dA cosine 0, okay, equals to Q n epsilon. E is constant, so E integral dA equals to Qn epsilon. So E A equals to Qn. What we have Qn inside the Gaussian surface here, inside this one, Qn equals to the total Q. Here, the total Q is inside the Gaussian surface. We can say Q total divided by epsilon. The area of Gaussian surface equal to 4 pi r square, because this sphere is at a radius or has a radius equal small r. So we can say here E equals to Q divided by 4 pi epsilon 0 r square. And you know that 1 over 4 pi epsilon 0 equals to K. Okay? K equals to 1 over 4 pi epsilon 0. So we can say E equal KQ divided by R square. It's the same result as before for the first method. The object can be considered as a point charge because from the external view, this object seems to be a sphere. Okay, so you can consider this object as a point charge.